What's up? It's your boy Quantum Pinguino back again with another video, and today we're going to be talking about my favorite integral. Off the bat, I'm going to show you guys the closed form answer of this definite integral, because the first time I did this integral was during a mathematics multiple choice exam, and when I saw this as one of the answer choices, I just didn't think that could ever be the answer. But when I actually did out the integral and got this answer, I got a very strong sense of satisfaction. Just as a quick clarification, the two brackets in the denominator stand for the floor function, which means that whatever you get from 1 over x, you round it down to the greatest integer that's less than or equal to 1 over x. So if I get 2.6, it goes down to 2. If I get 2.2, it also goes down to 2. So the first thing to do with this integral is actually just visualize it graphically. Off the bat, you see it looks like a step function, which means that you can approximate the area under each of the different steps as a rectangle. We see that the largest of the rectangles actually has a length of 1/2 and a height of 1. The next largest rectangle has a length of 1/2 minus 1/3 and a height of 1/2. And the next rectangle has a length of 1/3 minus 1/4 and a height of 1/3. As some of you may have seen coming, we can actually find a closed form expression for the sum of each of the rectangles, which comes out to the sum from n equals 1 to infinity of 1 over n minus 1 over n plus 1 times 1 over n. By distributing the 1 over n on the outside, we can then express our original integral as the difference between these two now independent summations. Starting with the summation on the right hand side, we can use partial fraction decomposition to split the original summation into two independent summations. After splitting our original summation, we can now start writing out explicitly the terms of our two new summations. Because of the minus sign between the two summations, we actually see that the terms start canceling out between the two summations in such a way that the only term that is non-zero is actually the 1 from the summation on the left hand side. As a result, we can conclude that the summation from n equals 1 to infinity of 1 over n times n plus 1 is actually just convergent to 1. So if we look back at our original integral, we see that the only thing we have left to solve is the summation from n equals 1 to infinity of 1 over n squared. However, this may be a bit more complicated than it seems at first glance. Finding a closed form for this summation was a highly contested problem in mathematics that was originally proposed by Pietro Mengoli in the 1650s, and took approximately 80 years for the one and only Leonhard Euler to solve the problem in 1734. It is aptly named the Basel problem, as it is named after the hometown of Leonhard Euler. Euler's proof starts as follows. First, do a classic Taylor expansion of sine of x around x equals 0. Then, simply take that Taylor expansion and divide through by x. Euler then applies something called the Weierstrass factorization theorem, which allows us to express a function, in our case sine of x over x, as a product of all of its linear roots. So, for example, since sine of x has zeros at x equals pi and x equals 2 pi, we can express it as a product of 1 minus x over pi times 1 plus x over pi, etc. We know that if a number is a 0 of sine of x, then the negative version of that number is also a 0 of sine over x. This allows us to factor a little bit further by, for example, taking 1 minus x over pi and 1 plus x over pi and factoring that into just a single term that's quadratic in x. Now we can collect the terms that are quadratic in x and factor out a negative x squared over pi squared from each of these terms. In doing so, we realize that we can express the summation of the factors, which are 1 plus 4 plus 9, as the desired summation that we're looking for, the summation from n equals 1 to infinity of 1 over n squared. Now, we have two expressions for the terms that are quadratic in x for sine of x over x. The one that we just derived using this whole Weierstrass function ordeal, and the original x squared term that we have from doing the Taylor expansion at the start. As these terms are both equivalent to the second order contributions of x for sine of x over x, we can set them equal to each other and actually solve for the desired summation to get the result that we expect, pi squared over 6. Now we have closed form expressions for the two summations we sought to solve, and we can prove that our integral is indeed equivalent to pi squared over 6 minus 1. And we can say QED. As always, thank you all for watching. I really appreciate the support, and until next time, happy Thanksgiving!